When we start thinking about reactions in a little bit, we're going to need to understand some things about the stability of alkene isomers. So let's take some time to look at those concepts now. So the discussion centers around groups of alkene or pairs of alkene isomers, meaning that the compounds that we're going to be dealing with and comparing to one another all have the same molecular formula. There's two things that we're going to think about. The first thing, or one of the things, is called steric strain, and we've seen this before. Groups within a molecule get too close to one another, they repel one another, and that raises the energy of the compound or the conformation. So groups get too close, they repel one another, and this raises the energy of the structure. The other factor that we'll consider is called the degree of substitution. The degree of substitution refers to how many alkyl groups are directly attached to the carbons in the double bond, which we'll call alkene carbons. So how many alkyl groups, which we can abbreviate as R, are directly attached to the carbons in the double bond. So we'll call those alkene carbons. Okay, let's look at steric strain first. This comes into play primarily when we're looking at the difference between a cis and a trans alkene. Remember, when we're making these comparisons, we always have to be comparing isomers. So the first example over here is the trans compound, or the trans alkene. And this guy over on the right is the cis. Now what we can see in the cis compound is that these methyl groups get too close to one another. And so that causes steric strain. So in this case, the cis compound, the cis alkene, is 10.6, not a number you need to memorize, kilocalories per mole higher in energy than the trans. And so we can extrapolate from this and make a general statement, which is to say that cis alkenes are less stable because of this steric strain. That means they are higher in energy if they're less stable. Than trans alkenes. Now remember, we have to be comparing apples to apples. So we have to be comparing two compounds that are isomers of one another, or more than two compounds, but they have to be isomers of one another. Okay, so that's steric strain. That tells us that trans is more stable than cis because the groups are farther apart in the trans compound, so they can't get too close. The other thing that we'll think about is the degree of substitution. How many R groups, alkyl groups, are attached directly to the alkene carbons? Okay, so remember again, we have to be comparing isomers. So in the set of alkenes that we're looking at on the screen right now, all of these are isomers of one another. Okay, so the R groups are all going to be different such that all of these things have the same molecular formula. Now, before we get started, let's draw in any missing hydrogens. So remember in the skeletal formulas, and these are examples of skeletal formulas, hydrogens are typically not explicitly drawn. Okay, so starting over on the left-hand side, here's an alkene where there are 4 alkyl groups that are attached directly to the alkene carbons. So we call that a tetrasubstituted alkene, And in a set of alkene isomers, that is going to be the most stable of the set. So this would be the most stable in a set of alkene isomers. The next most stable would be tri-substituted. So now we have 3 alkyl groups attached to the alkene carbons. And following that, in order of stability, we have 3 different types of di-substituted alkenes. The first one, which is the most stable of the 3, is the trans. The next one, which is less stable, as we saw previously, is the cis. And then finally, the di-substituted compound where both of the R groups are attached to the same alkene carbon. That doesn't have a name, but that's the least stable. It's about on the same order of stability as the cis, sometimes just a little bit less stable. So those are the di-substituted. And then finally, if there's only one alkyl group attached to an alkene carbon, we call that monosubstituted. And that is the least stable alkene isomer. So those are qualitative ideas. Looking at steric strain and the degree of substitution, we can use those 2 principles and easily put a set of alkene isomers in order of stability. Now we can also think about what we would do to what we would call quantify alkene stability. When we quantify something, that means that we're using numerical data to rationalize or explain, in this case, relative alkene stabilities. So using numerical data, to rationalize or explain a set of alkene stabilities. Now there's different ways that you can do this. You don't have to use the same approach every time, but the general approach is really always going to be the same thing, and it has to do with using data from a particular reaction. So for example, and this is what we're going to do today, you could use the standard enthalpy of formation. Now you learned about this in general chemistry, but just to remind you, this is the enthalpy change associated with a formation of 1 mole of a compound from its elements, with the caveat being that all the substances have to be in their standard state. So let's review that. That the standard enthalpy of formation is the enthalpy change associated with the formation of a compound so formation of, and specifically 1 mole of a compound from its elements and again, the condition being that all the substances are in what we call the standard state. Now, the standard state, you'll also recall, is just a set of conditions. So, for example, 1 atmosphere of pressure, 298 Kelvin. If you have molar solutions, their concentrations would be 1 molar, and so on. So we use the standard enthalpy of formation. So we'll talk more about that in just a second. But you could use other approaches as well. You could measure the heat of combustion or the standard enthalpy of combustion. So you could combust an alkene, see how much energy is released, and then compare that to the energy released by the combustion of other alkene isomers. Or you could use a reaction called a hydrogenation, which we'll look at later in this packet of notes, where you're attaching hydrogens to the alkene and converting it into an alkane. That also releases energy, so you could compare those energies as well. Using the standard enthalpy of formation, there's 2 possibilities. So first of all, let's look at this energy diagram. So if we're forming a compound from its elements, remember that our starting point is that the elements have heats of formation equal to 0. So we'll put the elements at the 0 line. So elements could combine in such a way to make a compound that's less stable than the elements. Okay, so that would be the energy level that I just denoted with the star. So let's say that's the compound that we just made. So here's the energy of the compound. And so the difference between the compound and the elements would be the delta H of formation. This would be an example of an endothermic heat of formation, meaning that the compound is less stable than its elements. And so that's going to have a positive value. And we can see that over here on the left side because of this plus. Now, there are compounds that exist like that. There's more than just a few. But what we're going to encounter are compounds that are that are more stable than the elements that are used to create them. So here's the energy level of such a compound. And this difference would be the heat of formation. That would be the energy released when that compound is formed from its elements. And this would be an example of an exothermic heat of formation. Which is to say that the compound is more stable than its elements. Because it's an exothermic reaction, the sign of delta H is going to be negative. Okay, so let's take these ideas and then we're going to combine them with what we know from the previous page. So here's a set of alkene isomers. So they're all C6, they have the same molecular formulas, and we also have the heat of formation data. Those are the numbers that are printed under each structure. We can go back and use the degree of substitution to predict the order of stability here. So the first isomer on the left is a monosubstituted one because there's only one R group attached to the alkene. The second one is disubstituted and cis. The third one is disubstituted and trans. The fourth one is trisubstituted. And then finally, the one over here on the far right is tetrasubstituted. Now we already know that the monosubstituted isomer is the least stable, and the tetrasubstituted one is the most stable. So we can already put them in order of stability because we know something about the degree of substitution. But now let's look at these numbers. So remember, there's a negative in front of each of these because each of them has an exothermic heat of formation. That means that each of these alkenes is more stable than the elements that were combined to create them. So if we plot this on a similar energy diagram to the one we saw just above, the energy level of the elements is 0. When the monosubstituted alkene is formed, we'll just say mono, 10 kilocalories per mole of energy are released. So that's from this number right here. When the tetrasubstituted alkene is formed, it's 16.6 kilocalories of energy that are released. So more energy. So this is the tetrasubstituted. So what we can see in the diagram is that more energy is released in the formation of the more stable alkene isomer. That corresponds with a larger negative value of the heat of formation. So more energy is released in the formation of the more stable alkene isomer. And that corresponds again to the larger negative heat of formation. Okay, so let's briefly touch on this question. Why are more substituted alkene isomers more stable than less substituted ones? This has to do with the fact that not all carbon-carbon bonds are the same. And we know from general chemistry that a shorter bond is a stronger bond. So in an alkene, the carbon-carbon bonds are going to be formed by overlapping orbitals if we consider using valence bond theory to explain this bonding. So let's remember the difference between an sp3 orbital and an sp2 orbital. The sp3 orbital is more elongated. Okay, an electron in an sp3 orbital, on average, will be held farther from the nucleus, the carbon nucleus, than an electron in an sp2 orbital, which is more squished down, more compact. So, all other things being equal, carbons that have different hybridizations are going to form bonds with differing lengths. So a bond between two sp3 hybridized carbons is going to be a longer bond, and thus a weaker bond. Than a bond between an sp2 carbon and an sp3 carbon. So those will be shorter bonds, which are stronger bonds. Now notice that there's nothing here that's saying that sp3 carbon-carbon bonds are inherently weak bonds. We're just saying that they're weaker than their sp2, sp3 counterparts. So if we were to count up all of the sigma bonds here in each of these alkenes, okay, each of them has a pi bond, so we don't really need to worry about that, because since they all have one, that's going to be a wash in terms of the energy. So the sp2, a bond between an sp2 and an sp2 carbon, we're talking about the sigma bonds, and so each of these is going to have one. That's just going to be the sigma component of the double bond. For sp2, sp3 bonds, the tetrasubstituted alkene here, which by the way we already know is the most stable, has 4 bonds between sp2 carbons, which would be the alkene carbons themselves, and sp3 carbons, which are going to be the carbons that are attached to the alkene carbons. So the tetrasubstituted alkene has 4 of those bonds. The trisubstituted has only 3. Using one of the disubstituted alkenes as an example, the disubstituted has only 2, and finally the monosubstituted has only 1 of those sp2, sp3 carbon-carbon sigma bonds. If we think about the number of sp3 bonds, then we also have to look at the rest of the structure outside of the double bond itself. So the tetrasubstituted alkene has 0 of those bonds. And let's use a new color for the new sp3 atoms. The trisubstituted has 1 such bond. The disubstituted has 2. And then finally, there are 3 carbon-carbon sp3 bonds in the monosubstituted. And remember, we also know that the monosubstituted is the least stable. So putting this all together, we recognize that the most stable alkene has the greatest number of strongest bonds. And the least stable alkene has the greatest number of weakest carbon-carbon bonds. And correspondingly, the lowest number of the strongest bonds.